And if the previous section established the airline model as the operational goal of the Raptor 3, we must now address the chemical reality that makes such a model physically possible. In the pursuit of rapid reusability, the greatest obstacle is not necessarily the mechanical wear of moving parts or the thermal stress of atmospheric re-entry. Rather, it is a silent, microscopic buildup of carbon known as coking. To understand the gravity of this issue, one must view the internal plumbing of a rocket engine not just as a series of pipes, but as a high-performance vascular system. If that system becomes clogged, the engine suffers the mechanical equivalent of a stroke. And the invisible enemy, understanding coking. Coking is the thermal decomposition of hydrocarbon fuels into solid carbon deposits. When a fuel like RP1, a highly refined form of kerosene, is exposed to the extreme temperatures required for regenerative cooling or pre-burner combustion, the heavy molecular chains within the liquid begin to break apart. This process, known as cracking, creates a sticky, tar-like residue that eventually hardens into a glass-like carbon shell. And consider the difference between a modern electric toaster and a traditional wood-burning fireplace. When you use a toaster, the heating elements glow red, transfer their energy to the bread, and then cool down, leaving the internal wires as clean as they were before the cycle began. There is no byproduct of the heat itself. A fireplace, however, is a dirty system. Every time you burn a log, a layer of creosote and soot accumulates on the bricks and inside the flue. If you were to burn that fireplace 10 times a day without cleaning it, the chimney would eventually choke, the airflow would vanish, and the fire would be extinguished by its own waste. And for decades, the aerospace industry accepted the fireplace reality of liquid-fueled engines. The Merlin 1D engine, which powers the Falcon 9, is a masterpiece of engineering, but because it burns RP1 kerosene, it is fundamentally a sooty engine. After every landing, the internal components of the Merlin, specifically the turbopump and the injector face, are coated in a layer of carbon. While SpaceX has mastered the art of cleaning and refurbishing these engines, the process remains a form of manual memory management. It requires human intervention to scrub the state of the hardware back to zero. To achieve the Raptor 3 goal of zero-touch turnaround, the engine cannot afford to be a fireplace. It must be a toaster. And Methane, the clean-burning API. The decision to use liquid methane, CH4, as the primary fuel for the Raptor was the first and most critical design choice in the entire Starship program. From a chemical perspective, methane is the simplest hydrocarbon, a single carbon atom bonded to 4 hydrogen atoms. This simplicity is its greatest virtue. And in a software environment, we talk about clean API is that return predictable results without side effects. Methane is the clean API of the propellant world. Because it has the lowest carbon-to-hydrogen ratio of any hydrocarbon fuel, its combustion products are almost entirely gaseous, carbon dioxide and water vapor. Unlike the complex, long-chain molecules found in kerosene, which can contain anywhere from 12 to 15 carbon atoms per molecule, methane does not have the structural complexity required to easily form the heavy polymers that lead to coking. And when methane flows through the regenerative cooling channels of the Raptor 3 nozzle, absorbing the hellish heat of the combustion chamber to keep the metal from melting, it remains chemically stable. Even as it reaches supercritical temperatures, it does not crack into solid carbon. It enters the cooling jacket as a cryogenic liquid and exits as a hot gas, leaving the internal veins of the engine as pristine as they were on the assembly line. This is hardware memory management at its finest. The system automatically clears its own state with every cycle. In thermal management and the resource leak problem to a graduate engineer, the impact of coking is best understood through the lens of heat transfer coefficients. In the regenerative cooling cycle discussed in Chapter 5, the fuel acts as a heat sink. The efficiency of this heat exchange depends on a clean interface between the fuel and the metal walls of the cooling channels. And when coking occurs, the layer of solid carbon acts as an unintended insulator. Carbon is an excellent thermal barrier. As a thin film of soot builds up inside a cooling channel, it reduces the ability of the fuel to whisk away heat from the combustion chamber wall. This creates a thermal resource leak. On the first flight, the wall temperature might stay at a comfortable 600 degrees Celsius. By the 5th flight, the insulating layer of coke causes the wall temperature to climb to 700 degrees Celsius. By the 10th flight, the metal reaches its fatigue limit and fails. And in a kerosene engine, the only way to patch this leak is to physically disassemble the engine and chemically flush the channels, a labor-intensive reboot of the hardware. The Raptor 3 avoids this degradation entirely. Because methane does not deposit carbon, the thermal state of the engine remains deterministic. The heat transfer profile of the 1000th second of flight is identical to the first. This allows SpaceX to push the Raptor 3 to much higher chamber pressures, exceeding 350 bar, than would be possible with a dirty fuel, because they do not have to leave a safety margin for future soot buildup. And the full-flow multi-stage advantage. The purity of methane is especially critical for the Raptor's full-flow staged combustion cycle. As we explored in Chapter 4, the Raptor utilizes 2 separate pre-burners, an oxygen-rich pre-burner and a fuel-rich pre-burner. In the fuel-rich pre-burner, a massive amount of methane is mixed with a small amount of oxygen to drive the turbopump. In a kerosene-based staged combustion engine, like the Russian RD-180, a fuel-rich cycle is nearly impossible because the hot, unburnt kerosene would instantly turn into a thick sludge of coke, seizing the turbine blades within seconds. This is why most kerosene-staged combustion engines are forced to use oxygen-rich cycles, which present their own nightmare of eating the metal of the engine through oxidation. And by using methane, the Raptor 3 can run a fuel-rich pre-burner with total impunity. The hot gas driving the turbine is essentially a clean, high-pressure methane mist. This allows the turbopump tolerances the microscopic gaps between the spinning blades and the stationary housing to remain incredibly tight. In the Merlin engine, these tolerances must account for the eventual crust of carbon that will form. In the Raptor 3, the turbopumps can be designed for maximum efficiency because the operating environment inside the pump remains surgically clean. And this leads to a phenomenon we can call performance persistence. In legacy systems, an engine's specific impulse, or ISP, and thrust-to-weight ratio would slowly decay over multiple test firings as the internals became fouled. The Raptor 3 breaks this curve. It maintains its day-one performance metrics across its entire service life because it never suffers from the bit rot of carbon accumulation. In eliminating the ground stack, the chemistry of speed, the move to methane, also solves a secondary problem that is often overlooked in the quest for the airline model, the purge problem. Kerosene is a liquid at room temperature and has a low vapor pressure. Once it enters a rocket engine, it wants to stay there. After a Falcon 9 lands, the kerosene remaining in the lines must be meticulously purged with nitrogen or helium to prevent it from gumming up the valves as it sits on the pad. If even a small amount of kerosene is left in a dead leg of the plumbing, it can vanish into a sticky resin that prevents a valve from opening on the next flight. And methane, being a cryogenic gas at ambient temperatures, is self-purging. The moment the pressure is vented, any remaining methane simply boils off and exits the system as a gas. There is no residue, no puddling, and no need for an army of technicians to spend hours flushing the system with cleaning agents. This self-cleaning property is what allows for the zero-touch interface discussed in the previous section. The engine wipes its own cache the moment it shuts down. And the Martian connection, a closed-loop ecosystem. While the immediate benefit of methane is reusability on Earth, the choice was also a strategic architectural decision for the future of the species. As discussed in Chapter 2, methane can be synthesized on Mars using the Sabatier process, combining Martian atmospheric carbon dioxide with hydrogen extracted from water ice to create methane and oxygen. And from a systems engineering perspective, this makes the Raptor 3 the first native engine of the solar system. If SpaceX had chosen a more exotic or dirty fuel, the Martian colony would have been forced to build massive, complex refineries to create high-purity propellants. By designing the Raptor to run on the simplest possible hydrocarbon, they have ensured that the fuel API is something that can be replicated on any planet with a carbon-based atmosphere. And furthermore, the lack of coking is a prerequisite for the long-duration sleep mode required for Martian transit. If an engine were to sit for 6 months in deep space with kerosene residue in its lines, that residue would likely undergo chemical changes, known as polymerization, that would render the engine a brick by the time it reached its destination. Methane stability ensures that the state of the engine is preserved through the long vacuum of interplanetary space. And memory management for physical hardware. To summarize the shift from RP1 to methane, we can look at it as the transition from manual memory management to garbage collection. And in the era of the Saturn V and even the Falcon 9, the engineer is responsible for freeing the hardware of its carbon byproducts after use. It is a manual, error-prone process that limits the uptime of the system. The Raptor 3 use of methane represents an automated garbage collection routine. The fuel itself ensures that no orphaned carbon atoms are left behind to clog the system's memory. And this cleanliness is the silent enabler of everything else. It is what allows the 3D printed manifolds to be so complex because they don't need to be accessible for cleaning. It is what allows the turbopumps to spin at 100,000 RPM with such tight clearances. And most importantly, it is what allows a starship to land, refuel, and take off again within the span of a few hours. And without solving the coking problem, the airline model would be nothing more than a PowerPoint fantasy. You cannot have a high-frequency transportation system if your planes require a complete engine overhaul after every trip. By choosing the clean-burning API of methane, SpaceX has moved the bottleneck of spaceflight away from chemical fouling and toward the next great frontier of engineering endurance. And as we have seen, the state of the engine's internal chemistry is now a solved problem. The veins of the Raptor 3 remain clear. However, even a perfectly clean engine is still subject to the laws of physics. While the carbon doesn't build up, the metal itself remembers every second of the flight. Every vibration, every thermal expansion, and every startup transient leaves a microscopic mark on the crystalline structure of the engine's alloy. This brings us to the final, and perhaps most difficult, hurdle in the quest for a 1,000-flight engine. And if the fuel is clean, the only thing left to fail is the metal itself. We must now turn our attention to the clock that ticks inside every engine. Number 9.3, structural fatigue. How many flights can one Raptor survive?